go over basically some concepts that you guys learned in algebra called domain and range. And then once we kind of talk about how to find the domain and range from roster notation of a function, an actual function listed out, or the graph of a function, we're going to get into graphing piecewise functions, which can be a little bit tricky. We'll take our time there. I'll do my best to go slowly, and then obviously we'll have some practice afterwards. Okay, so let's start with domain and range. Now, remember from last lesson or from your days in algebra that domain is the set of all values for the input or your x values. So I put the letter D, and then I'm going to put, in this case, because we are listing them, that's called a brace. And if I look at all of my x values, I'm going to put them in order from least to greatest. So 2, 3, 4, 5, and 6. All right, so that's my domain. Let's do the range. I know it doesn't ask for it. Let's do the range. All right, so the range is your set of all possible y values. All right, so it's 10, 10, 20, 30, and 40. Now, be careful here, right? The common mistake is to put 10 twice. But again, if you already have it, you don't need to list it twice. It's all possible values. So if I put the 10, that will take care of the first two y values. So then 20, and then 30, and then 40. All right, so that is our range. Let's do the same thing for these two functions. Now, I'm hoping you know what these look like when you sketch them. All right, this is a quadratic function, and that -1 has moved the parabola a unit down. So essentially it looks like this. All right, so this is that x squared -1. And if you look, you should notice that for the domain values, as you go from left to right, you can have any value for x and it'd be fine, right? You can plug in any number and square it and then subtract 1. So the domain is actually all real numbers, which you can write out all real numbers, or how we're going to do it is called interval notation, where I write -infinity to +infinity. That's how I'm going to write down all real numbers. All right, now the range is a little different. You'll notice that these arrows up here at the top, right, they're going up forever, all right, to +infinity, but I don't actually go down towards -infinity. You'll notice that my lowest y value is right there at that vertex, which is -1. So we do hit it. So you'll notice I'm putting a bracket around that to say that we do include -1 as our lowest y value, and our highest y value is going to go up towards +infinity. So that's how we do the range for that one. Let's try one more from the actual function. This is called a square root function. Again, I'm hoping you remember what this looks like. It's kind of half of a parabola, but on its side. And because of this -7 inside the radical, it's actually going to move this 7 units to the right. So it's going to start over here. And again, like I said, it's kind of a half a parabola, but on its side. All right, so the domain, and you probably could figure this out even without the sketch, right? But the domain, the lowest x value is actually going to be 7. And you can think about this. If I plugged in 7, 7 minus 7 is 0, and the square root of 0 is 0. But if I plugged in anything below 7, like 6.95, when I subtract that, I'll get a negative value. And we can't do the square roots of negative numbers. So that's why the lowest x value is 7. Going all the way to the right, anything greater than 7 is okay, so towards infinity. Let's do the range. All right, you'll see the lowest y value is actually 0. We kind of just said it as we plugged in 7. 7 minus 7 was 0. The square root of 0 is 0. And we include it, right? The dot is closed. And then even though it kind of doesn't really look like it, this arrow is going to every time get a little bit closer to infinity, a little bit larger number. So even though it'll take forever to get there, a long time to get there, we're going to say it approaches infinity. All right, now let's do that same thing, but from a graph. And this is where the Delta Math link is going to ask you to do from a graph as well. All right, so the domain, right? The domain is your lowest x value, which I see is -3. These don't have any arrows, right? They have circles. And then my highest x value is this +1 here. All right, what you should notice is this -3 is an open circle. So I'm going to put parentheses, and this +1 or 1 comma -4 point is closed. So I'm going to put a bracket around that. All right, now the range is tricky the lowest y value is actually this point or this point, and they both have a y value of -4. And we put a bracket because it's included. And then what students are going to do to mess this up is the highest y value is actually 0, right? This point and this point. But if you notice, this actually does touch it. So even though this one is open, this close point, or because we touched 0 with this part of that function, we are actually going to include 0. So even though you think, oh, wait, why is it not parentheses? Because we have an open point here, right? Because we have another point with a y value of 0 that does include it, we do have to include it in our range. All right, so that's it for the range. I think that's a little tricky, and you'll get some practice on the delta math. Okay, you can also practice these if you'd like as well. Okay, let's get into piecewise functions. This is going to be our graphing part of the lesson. And piecewise functions just means that instead of having your traditional one function for whatever domain, whatever range, we have usually 2 or even 3 or even more than that pieces of functions separated by different values for x. All right, and the best example is the absolute value function, which hopefully you remember from your days at algebra, is a v when you graph it. But essentially what this is that this is the line y equals -x, and this is the line y equals x for different values for x, all right, which is noted in that piecewise function. All right, so let's try to do this one. I'm going to show you the way to do this on the paper by hand, and then when we do the Delta Math link, you'll get a chance to practice using the paper to help you find points, and then the Delta Math link is nice because you can actually manipulate how the points look on the computer. So I'm going to start with the first piece, which is x squared, and I always make a t-chart for my x and y, and I want values that are less than or equal to 1. So I'm going to use -3, -2, -1, 0, and 1. And when I plug those in, I'm just squaring it. So -3 squared is 9, -2 squared is 4, -1 squared is 1, 0 squared is 0, and 1 squared is 1. All right, go to the next piece. It's actually just this y value of 3. And this one is a much easier piece because we need values between 1 and 2. Now, I'm going to write down the 2 because it does say or equal to 2. And I'm also going to write down the 1. You may be saying, but Mr. Frederick, why would you do that? Because it says to not include it there. I get it, but you're going to see that when I actually graph that point, I'm going to make it an open circle, which will allow me to get all the points that are less than 2, but greater than 1, like 1.1, 1.2, 1.3, all those points. Now, when you plug into this piece, right, the number is just 3. So the y value is 3 for both of those. And the last piece is x, and I need values that are greater than 2. Now, similar to what I did with that previous piece, you'll notice I am going to plug in 2, but like that previous piece, it's going to be an open circle at that point to show that we get all the points that are less than 3, but greater than 2. And these are just when you plug them in, you get the same value. All right, so let's start trying to plot this. Let me see, how do I do this? Let's use different colors. All right, I'll use orange for the first piece. All right, so this first piece is going to be orange. And all those points are going to be solid points because it does say or equal to. So when I do -3, 9, right, it's going to be a closed circle. Okay, and then -2, 4, -1, 1. It was 0, 0, and 1, 1. Remember, all those are filled in. Here's where it gets a little tricky. I'll use, let's use pink for the next one. So pink for the next one. And I'm going to plot 1, 3, and 2, 3, but because this doesn't have an or equal to underneath that symbol, I'm going to do an open circle for 1, 3. So 1, 3 is an open circle, and 2, 3 is a closed circle, and I can connect those. I'll connect the orange in a second. Forgot to do that. Sorry about that. And let's use purple for the last one. So purple for this one, and like the last piece, this point, or this doesn't have an or equal to for that 2, so this one will be an open circle at 2, 2. But then everything else is a closed circle. All right, so let's make this line. All right, so that's how we're getting kind of to the right forever. Let me make that orange again. All right, so this is that curve. parabola piece of the piecewise. All right, and then you notice I don't connect, right, each piece. You'll notice that the orange doesn't connect to the pink doesn't connect to the purple. In this case, none of my pieces of my piecewise function had any overlap, so that's why you can see all those open circles. Now here's the thing, guys, if you don't make those open circles open, right, if they end up being closed, then this would fail the vertical line test and would not be a function. So that's what you'll get a chance to practice on Delta Math, is to make sure to make all the pieces, but also making sure that whatever's open should be open, so that way you have a function. All right, so you'll get a chance to graph things like this. You can practice this one if you want on your paper. There are some exit ticket questions that you can help or practice. Ultimately, I'm going to steer you to practicing those Delta Math links on the domain, the range, and then graphing piecewise functions. Good luck.